You guys heard of classical mechanics, right? Well, it's all wrong. It's about quantum mechanics now.
But we need classical mechanics.
Shut up! Roll tape!
Roll tape!
Who are you guys?
We are the boundaries.
What? Let me out of here! Let me out of here!
You don't have enough energy to overcome us.
How much energy do you have?
We have infinite energy.
That last ASU lecture was confusing. What was he on about? Square wells? I thought the wells were round.
Not actual wells, boy. I'll explain it to you again, and this time pay attention. First off, look at this equation. It is the Time Independent Schrodinger Equation, or TIES for short. It is very important in quantum mechanics. Before we learn more about it, let me talk you through some of these pesky variables here. Mass of particle, position in field, potential energy as a function of x, and energy of the particle. Got that? Good. I bet everyone's wondering what this is, though. Seen it before? You better hope so, we've had 3 lectures on it.
Yes, it's the wave function given by the Greek letter phi.
In regular old classical mechanics, the position of the particle and its momentum can be easily measured. In quantum mechanics, on the other hand, particles exhibit wave-like properties when they aren't being detected or observed. We call this wave-particle duality. This means that we cannot determine its position or momentum because waves have neither. However, we can describe the position of the particle as a probability. The probability of each possible observation of the particle is determined by the wave function. All the information you need to know about a particle in a certain situation without observing the particle can be found by solving the TIES equation. Please note that the wave function has to be continuous, i.e. its first and second derivatives do not equal 0, otherwise the TIES cannot be solved and therefore its wave function is wrong. As you saw before, our little particle was free to roam. This was when she existed in a region of zero potential energy, meaning that the particle is not being affected by any force. So for an area of zero potential energy, the middle term of the TIES disappears and we can solve it as a differential equation that is in a similar form to the simple harmonic motion equation. The solution is A sine px over reduced Planck, where p is the momentum given by square root of e to m. As expected of a free particle, it can be found anywhere in x. In the video, you see the particle then encountering 2 boundaries, signifying areas of infinite potential. The particle would have to exert infinite work done in order to exist in these bounded areas. This is impossible so that they cannot exist beyond these boundaries. However, between these boundaries they still exist in zero potential, and therefore have the same equation as a free particle. Much later.
What happened to the other guys?
They went to the toilet.
You guys seem shorter.
We skipped breakfast.
Does that mean you guys have less energy? She's up to us! I'm getting through! I'm kind of getting through!
As you can see from the video, the finite square well is similar to the infinite square well, where instead of areas of infinite potential, there are areas of finite potential of U. U can be any value. If the energy of the particle is greater than U, then the particle has enough energy to enter the regions of finite potential, and still be described as a sine wave, but with a different value of momentum. P equals the square root of E minus U to M instead of the square root of E to M. In the video, however, we see the situation where the energy of the particle is less than the potential energy of the finite potential areas. Solving the ties for this case yields exponential functions for the finite areas. In the areas of finite potential U, we have the wave function being described as
AE plus or minus KX plus C,
where k equals the square root of the modulus of E minus U times 2m over the reduced Planck constant.
Yay, I finally get it, Professor. Thank you.
No problem, kid. Professor, away!
Now how do I do a line integral?